So we'll start by recalling the notions that will be used in this lecture. Let's see if you forgot the notion of compactness. Remember that K is compact, at least in our setting. So when we are in R, K is compact if every sequence xn in K, so a subset of K, has a convergent subsequence whose limit is also in K. So subsequence, say we can denote this x sub n sub K such that it is convergent, so xn converges to something, converges to a K, and that limit K is in the set, that limit x is in the set K. So this is the property. So whenever you have any sequence inside the set K, every time we have a sequence like that, completely contained within K, we can find a subsequence that is convergent and whose point, where it is converging to, the point it is converging to, it isn't K, then the set is compact. Now, remember, this is just to contrast things. So the concept of continuity at a point X, say in K, in a set K or in a set A, just to make the distinction. Was that so for a set X, we're gonna write everything and make everything explicit, dependence, so as to make sure that that we know what the differences are when we talk about continuity versus uniform continuity. So f going from A to R, yeah, so this is a function, a given function, we say f is continuous at a point A if for all epsilon greater than 0 we can find delta. Here the point A, and we're talking about a point A, so there exists at epsilon, no, for all epsilon greater than 0, this doesn't depend on anything, we can find a delta. This delta will depend on A and on epsilon. So in principle, it depends on the point where you're at. So if you want to conclude what's here, what's going to come, the delta may need to be adjusted or to be chosen smaller if you are at a point where the function is changing more rapidly, or and also very small when epsilon is getting smaller. If epsilon is small, then you typically want delta to be smaller than epsilon, or comparable to that. For all functions, delta, most of the functions you will need to consider, you need to take delta very small as epsilon gets smaller and smaller. Of course, if you have a constant function, then delta doesn't, it's irrelevant, but that's not the focus of our discussion. We are really trying to treat the difficult cases. So for every epsilon greater than 0, there is a delta. Delta depends on A and epsilon. Remember, such that if x minus A is smaller than this delta, then f of x minus f of A in absolute value is smaller than epsilon. Of course, this delta has to be greater than 0, otherwise this definition will not be saying much. So this, I mean, if you put in the context of uniform continuity, again, we have a function that is defined on a set A. Goes from A to R, and we say f is uniformly continuous at a point, no, not at a point, it's uniformly continuous on A, the set A, if for every epsilon greater than 0, there exists a delta, now depending only on epsilon, such that x minus y is less than delta, implies f of x minus f of y is less than epsilon. I mean, the absolute value of x minus f of y is smaller than epsilon. And this is true for all x comma y in the set A. So in particular here, if this is true for every pair, you may fix a y and consider just any x. X is your variable, and here you would be saying that for every epsilon there is a delta. It depends only on epsilon, such that x minus a is smaller than delta, like in the definition above. So here we have y, which we're letting vary, but here a above a is fixed, so we're looking at continuity at a point. Here we can fix the second point, point y, and then x minus that point a, saying absolute values being smaller than delta, will imply that f of x minus f of a is smaller than epsilon. So that in particular shows, and since y is arbitrary, so that a is arbitrary, we conclude immediately that if f is uniformly continuous, then it is continuous at every point. Because we can pick y to be equal to a for any a inside the interval, and then just concern ourselves with what happens when we move x. But more than that, notice here that this delta doesn't depend on anything, doesn't depend on x, y, or anything else. So that's what makes the continuity here, the concept of continuity here, stronger when we talk about uniformly continuous functions, because the same delta will work for every point inside the domain. So one example of a uniformly continuous function are the affine linear function. So if f of x is, say, 4x plus 5, then what is f of x minus f of y in absolute value? This is just 4x x plus 5 minus 4y plus 5, and this is exactly the same as 4x minus 4y. And the 5 here will cancel out, which is just 4 times the absolute value of x minus y. So if this is less than delta, if this is less than epsilon, say, over 4, then, so if, so if the absolute value of x minus y is less than epsilon over 4, then this product here will be less than epsilon, which will imply that f of x minus f of y in absolute value will be smaller than epsilon. So this is your delta here, epsilon over 4. This is your delta of epsilon that we found here in the definition. And you see, here nothing depends on, the delta doesn't depend on the point x and over y. Delta is just a delta of epsilon. So you can make sure that f of x minus f of y is going to be within distance epsilon, provided that x and y are close enough. Close enough meaning closer than epsilon over 4 in this case. But that distance here doesn't depend on the point x or the point y. Another example, so this is clearly uniformly continuous. So f is uniformly continuous. And f, and this is uniformly continuous on all of R, and in every subset of R as well, because no matter where you are or where you restrict your domain to, this condition, is the same. The condition of closeness between x and y, in order to guarantee that the images are sufficiently close, doesn't depend on x and y. Where you are. It just depends on the difference between the 2 points. Okay, so then next we see another example. In this case, so let's consider g of x from, and now we have to, in order to make sense of this example, in order to get the point that I'm trying to make, we need to consider as a function from the whole real line to, at least we need to have consider g defined in an unbounded set. G of x so let be x squared. So the function x squared, which is defined on the whole real line, will not be uniformly continuous. Why is that? Because g of x, say, minus g of y in absolute value is equal to x squared minus y squared in absolute value. This is the same as absolute value of x plus y times the absolute value of x minus y. And now here, of course, if we make, no matter where we are, and if x is close to y, say, then this is close, approximately equal to 2y. Again, we're just, we're considering the case where this is, where we're just looking at what happens near a point. So this is familiar to what you were asked to do for this week problem session. when you were to show that, that the function cube root of x is continuous, you get some coefficients which may depend on the point. So the point is to make sure, uh, since you want to ensure continuity and ensure that the images are close, you can first start with an a priori bound and say that x is at least, I don't know, within a certain distance of y to guarantee this is close enough to y. And so, of course, you have something that's closer to y and you're just moving x. Then this thing, as x approaches y, this whole thing is going to go to 0. And then, therefore, this thing here as well. Because here you're just moving x when you're looking at continuity at a point. But here, the problem is, for the function to be uniformly continuous, the delta you need to choose in order to guarantee that this is smaller than epsilon has to be uniform. So provided this x minus y, the distance between these 2 points, is less than delta, you're supposed to conclude then that the images here are are close enough. Actually, within epsilon distance from each other. Right. So the absolute value of g of x minus g of y has to be less than epsilon. So this is what you want. You want thing over here to be less than epsilon, provided this is less than delta. In fact, but look, if it were smaller than delta, if it were equal to delta over 2, say, then what you would be concluding here is that x plus y delta over 2, if delta is greater than 0, then delta over 2 is smaller than delta. So you will be saying then this, because here with our all equalities, if you want this to be less than epsilon, you want this to be less than epsilon. So what you would be saying is that this quantity here, 2 epsilon over delta, which may depend on epsilon or not, bounds x plus y for all values of x and y, which is impossible. Right? Just pick x equal to y, or really close to y if you want, because you want that to be you want this to be say delta over 2. So you can pick y plus delta over 2, which would give you inside 2 delta, 2y plus delta. And if y is positive, then this is exactly equal to that. If y is greater than 0. And you see here that it would be implying that y is bounded from above, while you can take y to be arbitrarily large. You can see what's going on here in the graph of the function x squared. For continuity at a point, what we want to say is, so this is the point A, say, and this is f of a, or g of a in this case. And so what you want is, maybe I need to move the point A here a little bit. So what I want is, when we're talking about continuity, what you say is you want to guarantee that the images of a certain neighborhood of A are within epsilon. So if you prescribe this, we would say this distance here is epsilon, then you want to go back here in the graph and want to say, be able to say then that there is a neighborhood of A like this, and well, this is actually our delta. This is our delta. I mean, the smaller of the two things is delta. There's two very small quantities here, but that's what. So the smaller of these two quantities is going to be your delta. So if your distance delta from A, and if you take the image of that point, then the image of that point is going to be within distance epsilon from G of A. Yeah, but you see that if the function is changing very rapidly, then that delta becomes really small. For instance, over here, for the same epsilon, you have a much wider interval. You have much wider intervals here than on this side. So here delta is bigger than delta over here. And if you move to the right, so if we zoom in, we'll see is something like this. So that's for very large values, you see that x-coordinates is changing very rapidly. So if we just move a little bit to the right from a point A, and this is the image of the point A, we're going to see a huge change in the values of the function. So it's clear if we want to be within a certain distance of that, then the delta we have to pick, so that how close do we need to prescribe the points to be to A, is getting, that neighborhood is getting really small. So you can never find a delta that works for all points, because the delta is actually going to 0 as x goes to infinity, or A goes to infinity. The deltas are going to 0, so you can never find like the minimum. If it's going to 0, you cannot pick a smallest one, because in fact you can always find a smaller delta if you move far to the right. So as I said, that's the point of defining, say, a uniform continuity. Is we want to find if here we don't want to have to choose a different delta. Like in here, for instance, we see that function is changing very rapidly. Then, in order to be within a neighborhood size epsilon of, neighborhood epsilon from the point G of A, so all the elements in the image have to be, G of x has to be such that G of x minus G of A in absolute values is an epsilon. In order to guarantee that, we need to choose a very small delta neighborhood of A. So to guarantee that all the points in that small delta neighborhood are within distance epsilon G of A. Okay, so that's what happens here with these two notions. Notion of continuity and uniform continuity. The big thing is, even though this function, if the function x squared is not uniformly continuous in the whole real line, because as we saw You know, as the function starts increasing very rapidly, uh, then the neighborhoods you need to choose are very, very small around a point to guarantee continuity. But if you restrict yourself to a compact set, then yeah, these neighborhoods gonna get smaller than at the endpoint. And in fact, that this is common for all continuous functions. I mean, not the fact that you have to choose things at the endpoint. I mean, the highest value at the endpoint. I mean, the smallest value. But there's going to be a smallest value. There's going to be a smallest delta. Not on the deltas are not going to zero if you pick any particular point. And that's the content of the next theorem. That's why combining continuity and compactness is a very important thing. I mean, it leads you to very important conclusions. So this is the theorem. Theorem 4.4.7, which is uniform continuity on compact sets. So what does it say? That a function that is continuous on a compact set K is uniformly continuous on K. So a uniformly continuous function, as we saw, I mean, it has to be continuous at every point, but the converse is not true. We saw with x squared, we already know that it's a continuous function, it's continuous at every point, but it's not uniformly continuous over R. However, if we're allowed to play with the domain, I mean, where we restrict ourselves to looking at a subset of the real line, and that set happens to be compact, continuity is the same as uniform continuity on compact sets. So if you're in a compact set and you have a continuous function, then that function is uniformly continuous inside that compact set. In particular on closed intervals. Remember, the closed intervals are the first examples of compact sets. You know, when studying topology in R, I mean, one of the first things we say, I mean, the characterization of compactness that we had, they're valid for R or Rn. The compact sets are sets that are both closed and bounded at the same time. So closed intervals or intervals that form a comma b, including the points a and b, are compact. So if you have a function defined there, then that function is uniformly continuous if it's provided it is continuous. And so for the proof, how do we prove this fact? Well, so the thing is, I mean, it always goes back to the definition. So remember, what are we supposed to prove? That given any epsilon greater than 0, there exists a delta such that the distance between x and y being less than delta implies that the images of these 2 points are within epsilon from each other. So let's assume this is not the case. So we need to negate everything. So for epsilon, for all epsilon becomes now there exists an epsilon, such that no matter what delta, so for all delta that we may choose, there are points there are within delta distance, and such that their images are at least distance epsilon from each other. So, but if you look at that, since that is true for no matter how small you pick delta, what you're saying is that you can find a sequence of points, also xn and yn. There are at distance greater than or equal to, less than delta n, say, or 1 over n if you want, and such that the distance between f of xn and f of yn is greater than or equal to epsilon. So assume we have two sequences in K. Xn minus yn in absolute value is less than 1 over n, and at the same time, if, let me just write it here, and f of xn minus f of yn is greater than or equal to epsilon. It's greater than or equal to epsilon. So okay, let's start again. Since I said it, I forgot to write it down, but it would let epsilon be a small number, a positive number. And now we assume we have two sequences, xn and yn, such that the xn minus yn is less than 1 over n, and f of xn minus f of yn is greater than or equal to epsilon. So using compactness, we're going to arrive at a contradiction. Right, so first thing to notice is because K is compact, there exists a subsequence x of nk such that x of nk converges to x in k. Now, x of nk converting to x in k implies in particular that y sub nk converges to x as well. In fact, when you look at, say, the distance between y sub nk and x, you can use the triangle inequality and use the fact that y sub nk minus x sub nk is smaller than 1 over n. K is smaller than 1 over nk plus x of nk minus x. I can't erase here something. This should be a minus here. I don't know what happens. It's not allowing me to erase. But this is, of course, this is going to 0. And this is less than 1 over nk, so this is going to 0 as well. Okay, so we have two subsequences. I mean, this is subsequence x of nk and y sub nk. They're both converging to x. So that means because f is continuous, f of x of nk is converging to f of x, and also f of y sub nk is converging to f of x. But then that would imply that this distance cannot be greater than or equal to epsilon for all n, because in particular for the n case, this difference, f of x n sub k minus f of y n sub k in absolute value is going to 0. So that's a contradiction, and therefore we um, we made a false assumption here that there is there are these two sequences such that the distance between xn and yn is less than 1 over n, while the distance of the images is greater than or equal to epsilon, for some epsilon, for some fixed epsilon, fixed from the beginning. So that's not true. So therefore the function is uniformly continuous on a compact set. And that's gonna be, I mean, that's it for now. Now let's now seems to be erasing things here. Right, so then we can then we continue then in the next video. But now we've seen everything that we wanted to say about I mean, the applications of compactness. Uniform continuity is very useful. I mean, knowing that continuity in a compact set is the same as uniform continuity is very useful. The next thing is just to look at continue with the intermediate value theorem and then move on to the derivatives, which I left for you as a reading because most of it is just Calc 1 stuff that you already know. The only new thing being the Darboux theorem, and then we'll conclude chapter 5. That's what's going to come next.